Hi, in this video, we want to take a look at categorical data prep. All right, the first thing I want to say about this topic is not covered enough in curriculum. Absolutely, this is just skipped over. This is ignored. This does not get presented well enough. People don't talk about this, and you can get a lot of good stuff out of your data if you know how to handle categorical data. All right, so categorical data is going to be something like red, blue, green. Male, female, black, white, Hispanic, Asian, Native American, Pacific Islander, multiracial. So there's no inherent order on these items. Now, I know some of you will say there's an order on male and female. I think that joke is funny, but really, there's no order on this. So when we have this data, it needs to be prepared well if we want good models. I mean, that's right. Does that sound sensible? That if I want good data, if I want good models, I have to have good data. All right. So imagine a situation that I'm having, let's say, weather, and I've got zip codes. Now let's think about how many zip codes are in the United States. There's a lot. And if I want to start using like zip code as a predictor variable on weather, which would be very reasonable, right? We could say that Seattle will be colder than Orlando, more than likely. Don't know that it's not 100% true, but statistically speaking, we believe that Orlando's zip codes will be warmer than Seattle's zip codes. Okay. So if I have a whole bunch of different, zip codes from through the entire country, if I think about how many levels I have, that's a lot. There are going to be a lot of zip codes, and it'll be to the point where there's so many different levels, it's going to choke out the computation process. It's not going to be actually useful if I attempt to use this. So I need to do something about it, right? All right, so maybe I should combine all of the Orlando zip codes together. Maybe I should combine all of the Seattle zip codes together. All right, that makes sense. Yeah, could do that if the target variable is weather. Now think about another situation. What if it's financial that we're looking at? So maybe I want to predict the median household income. Now, think about a wealthy neighborhood in Orlando, a wealthy zip code in Orlando, and a financially depressed zip code in Orlando. Should we merge those together? Well, they're geographically close, but if it's a financial target variable, then I probably don't want to put poor and rich neighborhoods together, right? I would be better off actually putting the Seattle financially well-off zip code with an Orlando financially well-off zip code than I would be for putting things geographically close. So if I'm going to go through and combine levels on categorical data, I want to think about my target variable. Geography is not enough. All right, so when we go through and we do data prep on categorical data, our biggest number one tool that we have is going to be combining levels to a point where the number of levels is manageable for my project. And that's going to be the big one. That is our number one tool. Now, I'm going to start reading off some stuff because there's some stuff I put in the document that I feel is important, but as I'm talking, I can't remember what I put down. Okay, so many model structures cannot handle non-numeric data. All right, so I know that if you go in and you go into R, you go into SAS, you go into SPSS, and you have a categorical column and you put it into a linear regression model, it's going to spit out that model. But it's not doing what you think. What it does is it actually converts that categorical data to a bunch of numeric columns. And then it runs linear regression on the numeric columns. So a lot of model structures can only handle numeric data. So this includes neural networks. This includes linear regression. Okay, so if I want to get good linear regression models, if I want to get good generalized linear regression models, or any type of linear regression-ish models, or a neural network model, if I want it to be good, I have to think about data prep in terms of linear regression. and making everything numeric. So a lot of this is actually done under the hood. So what it will do, if I pass these categorical columns to the modeling function for the training, it just does it automatically. I don't see anything, I don't know about it. It just gives me the output. Well, if I'm going to be doing model after model after model, then each time, each individual model has to do this convert from categorical to numeric. And then the next model converts from categorical to numeric in the same way. And the next model converts from categorical to numeric. And it keeps on doing this over and over and over. And well, that's redundant, right? So what I could do if I want to speed up the process is I could manually do this conversion myself and then pass that to the modeling functions. And that way it'll be faster if I'm doing repeated modeling over and over, which is something we will be doing if we are on a big project with machine learning or predictive analytics. All right, so here's a good rule of thumb for imputing categorical data. So remember, imputation is when I fill in missing values with a surrogate. Well, what I like to do for my surrogate, if it's appropriate for the situation, also depends on the amount of imputation I'm doing, I like to put in missing or unknown. In this video, I'm going to use unknown because unknown is used elsewhere in the data. So I just slap in unknown to be consistent with what's already there. When I don't have like an unknown level, I usually use missing. That way, as I'm working through, I know that that was a missing value. All right, so now when I'm working R has some wonkiness when it comes to factors. Okay, so in general, I like to work with character strings instead of factors. Now, one thing that's nice about this is I get all aspects of string manipulation, can handle factors, and I can just execute that. So that's a very nice feature of having things in character strings. Now, if I'm going to have to use factors, I wait till the latest moment possible, and then I do a conversion. That's usually my rule of thumb as I work on projects. Factors will, really, you want to use character strings unless you have a non-alphabetical ordering. So let's say my categories are low, medium, and high. So that's ordinal data. Now, if R sees low, medium, and high, it's going to assume it's alphabetical order. So let's see, that would be high, low, medium. That's an incoherent ordering, right? So there I would need to use a factor, but I would wait till late in the project to make that conversion personally. Now, another time that I will be using factors is there are functions in R that only accepts factors and will not accept character strings. And in that case, I go ahead and I use it. Now, one thing I do when I load my data, I try to never load factors at all because they're just kind of clunky, they're difficult to work with. So I just go ahead and try to load everything as a character string. In fact, a lot of times on my data sets, I load everything as a character string. So these two commands will do this. Here, this is if I'm using base R, the call classes equal character. If I'm using the read XL package, then call types equal text will read everything as text. And then I convert my numerics to numerics, my integers to numerics, and I convert manually. I find that that's a good way to go because, you know, like if I had social security numbers, R will read those as numbers, but those aren't numbers. Those are categorical labels. They're ID variables. So I don't want R thinking we can do addition, subtraction, and so on with those. All right, so if you have to work with factors, use the forcats package in the tidyverse. It cleans up a lot of the issues. Now, if I have big data, factors are better than strings in terms of memory. So if I have a big data project, it's actually better to keep everything as a factor because of under the hood how it's stored. And I can use as character to convert factors to character strings or numbers to character strings easily. All right, so here are two contradictory statements. There's advantages and disadvantages to each of these. Okay, so if I have categorical data, let's say education is coded as 1, 2, 3, 4. So like 1, didn't graduate from high school, 2, graduated from high school, 3, some college, 4, graduated from college, 1, 2, 3, 4. Now, if I'm working with those levels, 1, 2, 3, 4, and I'm looking through it and I see some output, does that tell me what I'm looking at? I have to go back and refer to what the coding means. And if I have a lot of different categorical columns and I see 1, 2, 3, 4 as the coding, that's efficient memory wise, but you know what? I have no idea what these really mean. I have to go back and refer back to a data dictionary, and that slows things down. And really, I'm going to have to make before I do my visualizations, before I create a table that a decision maker could actually use, I have to, I have to get a crosswalk to convert. So if I'm doing something for presentations, if I'm doing something for inference, we want explicit labels on our categories. Now, in the opposite direction of this, of what I just advised you, integers and numeric data are better when it comes to speed and when it comes to computation time and in memory. So because of this, if I have a big data project, coding things as 1, 2, 3, 4 will be advantageous. So there's advantages and disadvantages. We need to be aware of which direction we want things to go in. All right, so let's talk about data prep of categorical predictor variables in supervised learning. So I have categorical data to predict a target variable. So here are our major options. First and foremost, if a categorical variable has 2 levels, I convert it to zeros and ones, binaries. So like smoker, yes or no, 1 for smoking, 0 for not. We could say gender or sex. Then I could say maybe female is 1, male is 0. That will work out. That's very nice. Now, extension of this is that we could create binary vectors when I have 3 or more levels. These are called dummy variables. So here we are creating a vector that records, is the categorical variable equal to at one particular level? And it's a 1 if it's at that particular level, a 0 if it's not. And in general, if we have n different levels, we go n minus 1. We will always have that. So the one that is missing is our reference level. This is the standard in linear regression. Now, a major tool in our tool belt so let me back up. So dummy variables, this is the classic statistics way of handling categorical data in linear regression and in other models. Now, if you think about this for a moment, think from a matrix algebra point of view. I'm taking categorical data. So let's say I have, red, blue, green as my categories. I'm going to create, 3 minus 1, 2 dummy variable columns. So I'll make a column for blue. If the vector is blue, then it's a 1. It's 0 if it's red or yellow. I'll make a column for yellow. It's 1 if it's yellow. It's 0 if it's red or blue. Okay. So now, what if I had like zip codes? How many distinct zip codes are there? There's thousands and thousands. If I do dummy variables on this, I'm going to have thousands of columns generated. Is that a good idea? Probably not. All right. So one thing that I don't like about dummy variables is I take the least informative type of data, categorical data, and it gets the most columns in my predictor variables. Does that sound off? All right, so from a linear regression point of view, or sorry, a matrix algebra point of view, I am the vector with the least informative data gets the greatest linear span. Does that sound right? No, it doesn't. Now, another thing to consider is that the more predictor variables I have, the more likely I am to overfit on my model. Always remember that. Keep that in your mind. The more predictor variables I have, the more likely or more prone, more vulnerable to overfitting I am. So dummy variables, which can blow up the number of columns, can make me very prone to overfitting. So that's a huge risk. So this is something we need to be mindful of. And so this overfitting aspect, because of predictor variables, is why I personally do not like dummy variables. Now, if I'm dealing with classical statistics, if I'm dealing with old men who learned, statistics back in the 50s, and they did things in the in the 60s and the 70s, and they want things to be done exactly how it was done during the Apollo missions, then I have to do it that way. I don't have a choice. But for modern data analytics, we have some other tools. I'm going to talk about those other tools. So the first one is to combine levels together, and we're going to call that binning levels. So if I have 3 or more levels. So let's say I have the colors red, orange, yellow, green, blue, and violet. I could put red with orange, yellow with green, blue with purple, right? I could bin those together if that makes sense for my project. So remember, when we go binning, we need to make sure that we put things together that make sense. Another option we have is to convert unordered levels to ordered levels. Now, this is one of those things that those classical statistics, classic statisticians will scream at you for. They will hate you for this. They will think this is terribly bad. Okay, I'm going to propose that for machine learning, this is a good idea or something we should consider in our tool belt. Maybe we use it, maybe we don't. All right, so my proposal is that you use the conditional average. So I have unordered data and I have, let's say, a numeric target variable. What I could do, I could take the conditional average of the target variable to define the order. So if I have red, blue, and green, and I have a numeric target variable, I take the average of the target when this one is red, the average of the target when this one is blue, the average of the target when this one is green, and then I use the order of the averages to define an order over here. Why would we like to do this? Well, if you look at the way that tree models are computed, they're trying to split the predictor variable into 2 groups, and that's how they split things. So if I order my levels in this manner, I'm setting it up so that it's easier for tree model training to split the data. Now, there is a loss. Now, it could be that I could actually make my model worse by doing this, but my experience is that I haven't seen like any real loss from trying this, but I have improved computation time quite a bit because of how the models are fitted. In your machine learning class, you'll learn about how like the steps it takes to split categorical data in a tree model, and you'll be like, wow, that takes a lot more steps, a lot more trials than it does for numeric or ordinal. Now the next one is called categorical smoothing. Here, what I'm going to do, I'm actually going to get rid of my categorical vector, and I'm going to replace each level with the conditional average of the target variable. So I'm taking that column, and at each level, I replace it with the conditional average for that level of the target variable. And then that's my new vector. And remember, numeric data is almost always processed faster than other types of data. And this will work just as well in terms of fitting as converting to unordered or converting to ordered levels. So this one I personally don't use. Categorical smoothing, this is one I like a lot. Also, I find that this is a good choice when I'm doing variable selection, because what I have found is if categorical smoothing vectors are useful in like the pre-screening of variables, then the original categorical data will be useful also. If categorical smoothing vectors are not not useful, then usually in my experience, the original categorical data dummy variables are not going to be useful themselves. So something that I have personally done, I've used categorical smoothing to screen out categorical predictor variables, and then I spend time binning, and then I convert to dummy variables. And now this is a really good step if I have a lot of predictor variables, because if I convert to dummy variables, then I have even more, and it's too much to wade through. All right, so some notes regarding converting to ordinal or numeric. This is not the classical statistics method. Do not use this if you have like old statisticians evaluating your work. Do not do this if you're working in actuary. Do not do this if you're working with financial oversight stuff. Like the people who look at it will absolutely have an aneurysm. Don't do it. Do not do categorical smoothing with people who will not accept it. A lot of classically trained statisticians will absolutely rupture a blood vessel in their head if they see you do this. But this is a good technique for model and data exploration. So you can use it to explore things, but don't include it in your final model. Like, see which ones are good, then go back to the original format of unsmoothed data and use that. All right, do not do this if you're going to be doing hypothesis testing. Absolutely do not use this for hypothesis testing. This will not work. And so if you need to do like classical statistics, if you need to do hypothesis testing, if you have an older classically trained statistician as a supervisor, make sure you use dummy variables as your final output. All right, so models that do not alter categorical data, such as tree models, they are going to take a long time to figure out the splits, honestly, or the best way to handle that categorical data. All right, so if I have, 3 levels, then, if I want to split that, there are a total of, see, it's going to be 7 different splits. So 2 to the power of 3 minus 1. There are a total of 8 possible subsets of the levels, and then we're not going to use like a full one way or another. So there are going to be 2 to the 3 minus 1 possible ways to do the split on that variable. This can take a long time to compute. Imagine if I have 10 distinct levels. 2 to the 10 is a big number. Also, categorical vectors and dummy variables can be really difficult to interpret and can make variable selection nearly impossible. I find that you should use categorical smoothing for variable selection and then use dummy variables if it makes sense. All right, so for this example, let's go ahead and load some data. I'm going to use the Nashville housing data set from Kaggle. And I'm going to strip it down to the target variable of sales price. Then I'm going to have 2 binary vectors. And then I'm going to have 3 categorical predictor variables with more than 2 levels. So these 2 have categorical data with 2 levels, and these 3 have more. And let's take a look at the data real quick. So notice that neighborhood is coded as a number, but is neighborhood a number? No, that's a label. It's like social security number. It's a label. This isn't, it's not going to work to use this as a numeric variable. So now let's go ahead and clean things up. So one of the first things you'll want to do if I have categorical data, a lot of times people will be inconsistent in how they record things. So if someone uses like the word school, another person puts SCH as an abbreviation, another person puts SCHL, dropping the vowels, R will interpret all those as 3 distinct different terms, 3 distinct levels. What we need to do, we need to clean things up using string manipulation to improve things. We will talk about string manipulation when we get to text analytics. So I just did some quick things. I made sure that all the punctuation characters are replaced. I made sure that the spaces were collapsed to underscores, so I have everything syntactically correct. And then I impute missing values with the term unknown. That way, when I look, I know that's an unknown value. I find that this is a much better choice than other choices for imputation. All right, so now let's go ahead and convert to binary. So here, sold as vacant has no or yes, and here are the numbers. So we can see that maybe about 10%-ish of it is yes. And so I'm going to convert it as numeric. Now, why do I do that? So really, if I need to explain something, if I need inference, it's better to have it yes, no than 0, 1. But for the purpose of machine learning, having categorical data is an extra step of processing. I'm better off with 0 ones. It'll process faster, and I'll be waiting around less. And remember, if I have to sit and wait for things, I can't explore better models if I'm waiting. So that's something that will come up in your career. Now, basically a very similar story, nearly the same proportion of yes for multiple parcels. All right, so now what I want to do, I want to convert neighborhood to dummy variables. Now I'm choosing neighborhood to show you why I don't like dummy variables. So I look here, okay, I'm going to use the fast dummies package. I'm going to use dummy columns, and I'm going to convert neighborhood to dummy variables. All right, so if I look here, we can see that we have, a bunch of different levels, right? Like the rows 4, 5, and 6 are all in the same neighborhood. So let's look down here and see that was 3130. And so now I can look through, and these are my dummy variables. So these are only one when when it's at the proper neighborhood. So let's look down. Let's try 3130. And everything's in alphabetical order. All right, so 3130, we can see that rows 4, 5, and 6 are ones while everything else is 0. So every time the neighborhood is 3130, it's a 1. Every other time it's a 0. If I look through here, holy cow, that is a lot of columns. It generated a bunch of columns for me. This is too much to use. Like this is, and remember, if I'm doing predictive analytics, if I'm doing machine learning, data mining, the more predictors I have, the more prone to overfitting I am. So I have to watch out. If I use this data as is, I am exposing myself to overfitting very severely. So let's go back up and let's take a look at some of the options in this. So select columns. Here I can just specify like which ones I want. So there's only one column in the data set, so I don't need to worry about it. Now remove the first dummy. So remember a moment ago I said that if you have n levels, you'll get n minus 1 dummy variables. So here, this false and this false is saying don't remove it. So I want, if I have n levels, I get n dummy variables. So I do not have a reference column. Now, if I'm using a linear algebra model, such as linear regression, I want to drop one of the levels, more than likely, because the intercept will cause mathematical problems with linear span. You don't need to understand that. Just know that if you're going to have an intercept, you want to go n minus 1 every single time. And we have the option of creating a column for missing values also, but I already took care of that with the unknown level. And here, split, what this will do is that if I have the situation where, let's say we have like pets, a column of pets, and we have dog, comma, cat, and we have cat, comma, fish. Well, in that situation, and that's just in one column, I would want dog to have a binary column, cat to have a binary column, fish to have a binary column. And split is saying what character in the character string do we split on. And remove selected columns. All right, this is false. So you'll notice that the original column is included in here. So the original neighborhood column is right here. If this was true, it would not be there. So by putting false, I have one column that's categorical. If it was true, I would have 100% binary vectors. All right, so now I just want to show you, if I take the row sums, so I take everything except for the original column, I take the row sums, you'll notice that they all add up to 1. They all add up to 1 because each each level is appearing one time. Okay, and then I can look and see if I want, I can add up for each of the dummy variables, how many times is it equal to 1? And we can see, I could go through and I could count. This is equivalent to seeing how many times a neighborhood appears in that column. And so just to show you, if I was to run table on the original Nashville neighborhood column, I would get a long table, and I grabbed only the columns that correspond here, and we get exactly the same number. So what I'm trying to show here is that the information that's from the table is preserved by using fast dummies, as long as I don't drop any columns. And here's my dimensions. All right, so this created 205 columns for me. So 204 dummy variable columns. If I removed a level, it would be 203. That's a lot. That's a lot for the size of data. That would make me very prone to overfitting. Do I want to proceed with this? Probably not. All right, so what I would want to do, I would want to bend things together. Now, when I bend things, we really have two choices. One is to use subject matter knowledge. So in this situation, I'm interested in tax district. I'm going to look at the tax district, and I'm going to think about putting them together using some other knowledge. Oh, okay. So when I am bending, my personal rules of thumb. Oh, this did not line up the way I wanted it to. Darn it, darn it, darn it. All right. So my personal feel is that every level of a categorical vector should have at least 30 observations, and all levels should be at least 10% of the total observations. Why do I do this? So if I say all levels should have at least 30, do we remember 30 from introductory statistics? What we want to do, we want to make sure that any parameter estimates, any conditional statistics have converged. So I want things to converge in the mean for sure. So I say at least 30 for each level. Now, I want to have all levels have at least 10% of my observations, at least 10%. Now, why do I do this? And this is so that we don't have too many dummy variables, because if I have a lot of predictor variables, I'm more prone to overfitting. This is to protect me from overfitting. All right, now, if these two are not achievable, then what I personally do is I do the best I can, but I make one single binary vector off of it. And that's that could be very, very severe binning, but it's better than causing problems in my predictive model. Because remember, my goal is to build a model that is a crystal ball and good for predictions. All right, so let's look at tax district. Now, to make things a little bit easier, a little bit easier to read, prettier, I just go ahead and get rid of some terms that don't add additional information to us. And so I remove the city of from tax district names, and I remove services district also. And so here we can see these are the distinct tax districts of Nashville in the data set. Okay, well, notice that Berry Hill only has 21. So in the data, there's 21 residences or 21 addresses in the entire data set. Well, is that enough for my rule? Well, if I say at least 30, no, it's not. So I need to combine it with another one. So here I'm going to use subject matter knowledge. I'm going to go and I looked up the different neighborhoods of Nashville, and I concluded that Berry Hill and Oak Hill were relatively similar enough to each other that I could put them together into one bin. And so here, whenever the tax district was in this vector of Berry Hill or Oak Hill, I replaced it with a new level of Berry Hill, Oak Hill. And so now I have a new table. So now we can see that, oh, and I sorted it, where'd it go? Berry Hill, Oak Hill now has 414 levels. So now I have at least 30 levels for each of my predictor variables, or for each of my dummy variables. So, okay, so that's good for the convergence and the mean aspect. But let's keep on going a little bit further, because remember, I personally want to have every single level have about 10% of my data. So what I'm going to do, I'm going to combine ones that have similar target variable values. So let's take a look at the conditional average. I'm going to use the median because we're talking about financial data. And in general, you just use the median anyway, because it doesn't suffer from skewness problems. The only time you don't want to use median is when you have distinct values and like integers with just a few levels to them. All right, so here I'm going to, so in the modeling, I would be using the log of sales price, and I want the conditional average of log sales price by tax district, and we're going to be taking the median, and I went ahead and sort it so that I can know what's going on. So here we can see that general has the lowest median log sales price, then Goodlettsville, then urban, unknown, Berry Hill, Oak Hill, Forest Hill, and Belle Meade. Okay, so at this point, one thing I like to do, I like to look at box plots. And so I can look to, and I can see that here, I don't have a lot of observations in Belle Meade. I still don't have a proportionately lot of observations in Berry Hill, Oak Hill. I don't have a lot of observations in Forest Hill, and I don't have a lot of observation in Goodlettsville. Now here, honestly, I'm satisfied with general, unknown, and urban. I'm good. Those I'm satisfied with. I'm not going to alter those at all. But when I consider the proportion, what I'm going to do, I'm going to go ahead and take Berry Hill, Oak Hill, Forest Hill, and Belle Meade and put them together. So let's look at where they were in my median. So I noticed that Berry Hill, Oak Hill, Forest Hill, and Belle Meade all have the largest conditional averages. Okay, so what I'm looking at this, and this is bigger than unknown, urban, and general, and these were like the big ones. So unknown is a pretty big chunk of the data. So that tells me that overall, these are relatively more expensive homes. So let's go ahead and put all three of these together. Also, the medians are relatively close to each other. Could be closer. So here, I'm going to bin all of these into one level. And I look at it, and I look at general and Goodlettsville, and I see that the median values and the box, the boxes in the box plots are parallel to each other. And I want to combine Goodlettsville with something. So general looks like a reasonable choice. So then I'll put them together. Now remember, this is for the purpose of machine learning or predictive analytics. This is not the purpose for inference on certain, well, it could be for inference, but if I'm reporting to, let's say, like the mayor of Nashville, they're not going to want to see me merge things like this. But when it comes to building predictive analytics, I probably want to do this. Otherwise, I'll have too many levels to make things sensible. And now when I'm binning right now, I'm really focused on using dummy variables. And so I can take a table and look to see, all right, so this is still relatively small, but at this point I'm satisfied because these levels, the conditional average on these were far enough from the rest that I think, hey, don't combine them with the others. And these were large enough that I'm just not going to sweat it. All right, so now let's look at the medians. So we can see that the wealthiest neighborhoods are the ones that are together. Then we have unknown, urban, and then general and Goodlettsville. By the way, I don't know anything about Nashville. I don't know if this is correct, but usually when I talk to people about my analysis and they're familiar with the subject, usually people tell me that I'm spot on. So if you're from Nashville, go ahead and let me know if this makes sense or not. All right, so now let's take a look at the box plots. So now you'll notice that we have a wider box plots. So something I'm doing, I'm using bar width equals true because that gives me visually how much data I have. Wider box plots, more data. Narrow box plots, very little data. All right, so now let's do categorical smoothing. So let's look at neighborhood again. All right, I do not want to manually go through and bend these. I can't. It's not possible. It's just too much for me to do. And so bending really isn't an option on neighborhoods. There's just too many of them. And also, I can see, you'll notice that here's a table. Like this neighborhood appears one time in the data. This neighborhood appears one time in the data. This neighborhood appears one time in the data. All right, like I'm not real sure is that that one observation is representative of the entire neighborhood, right? It might be representative, it might not be. I don't know. So if I'm going to bend off of one observation, it's gonna, I'm gonna have to take kind of like a leap of faith, and I'm not really willing to make a leap of faith. All right, so here's my game plan. I'm going to replace the neighborhoods with a measurement of central tendency. So for the moment, think of it as I'm going to replace the neighborhood with the average sales price. All right, that sounds reasonable. Going to replace the neighborhood with the average sales price. Now, average off of one observation. Is that going to be a reliable number? No. So here's what I choose to do. I'm going to take the average for the neighborhood. I'm going to take the average of the entire data set. I'm going to take a weighted average. So the weight on the data set average will be the number of rows of data, and then the weight on the neighborhood average will be the number of homes in there. And then I'll do a weighted average. And so that way, what will end up happening is that all of these values with just one observation, their weighted average will be pulled towards the overall average of the data. And so I'm really not, since it's going to be closer to the data or closer to the central tendency of the overall data set, I'm not letting it have a strong voice in my modeling procedure. I'm not going to let it have a lot of leverage because there's only one value in there. And we can just scroll down and we see that's just way too many. We see the unknown is pretty common. All right, so here what I'm doing is I'm taking the median of each neighborhood, and what I'm doing here, here's the median of each neighborhood, here's the number of times each neighborhood appears, that is its weight, and then I'm taking the median of the entire data set. And then I'm taking a weighted average of the medians. And so I find that this is a good way to go to prevent outliers that just happen to be there from pulling your model away from where it should be. And so now let's take a look at what we have. So now neighborhood becomes a much cleaner number, and you'll notice that everything is like only like unknown and neighborhood 4026 really will be able to get far away from the overall average of the data set. And for the purpose of machine learning, this is good. Now for inference, like if I need to report something about the neighborhoods directly, this would be a very poor choice. But for supervised learning, this is a good idea. Now, I've come up with another tool. I've never seen this anywhere. Oh, by the way, for categorical smoothing, I am not the author of it. I've never seen it written down anywhere. I have looked, but I got it from Professor Morgan Wang at the University of Central Florida, my data mentor. And so if you're going to credit somebody with that when doing it, credit him. Now, here I come up with a method of doing hierarchical clustering on levels using p-values and Wilcoxon signed rank tests to get p-values give us a pseudo distance matrix after some finessing. So what we're going to do, we're going to take, okay, so this isn't useful. Let's look through here. All right, so if I want to start combining things, if I want to start doing clustering, we can see that we have different number of values and different median values. So here I don't have a lot of faith in this number, but it's the only one I've got to work with for the purpose of binning. So what I'm going to do, I'm going to take the p-value from Wilcoxon pair rank test, and then I would take the p-value, I take the negative log of the p-value to get a pseudo distance matrix, and then I do hierarchical clustering on it, and now I can see how these group together. So if I was to do binning, like right off the bat, I would see office building 1 or 2 stories, nonprofit charitable services, or strip shopping center. These are all relatively similar sales prices. So for the purpose of binning levels together, these 3 might be a good choice. Now remember, I only want to bin when I have less than 30 observations and less than 10% of my total data. If a level is above that, I'm probably going to avoid binning it. And so another example, nightclub lounge and duplex have similar sales prices. So for the purpose of modeling sales price, it might be a good idea to put these together. Might not be. And it is possible to automate it, but I honestly don't like the automation aspect. I think you should do it slowly, but this gives us a good way of working through it. And this is kind of technical to work through it, but I think it is worth taking a serious look at. All right, well, that's all I've got for you. Take care and goodbye.